XKCD comic about how leap years mess up the measurement for a light year? Do you evaluate a light year based on a leap? Whatever. Feel free to look it up. So we are going to finish up conservation energy today, which is great. Kind of quick, which is nice. That's going to give us more time, so we may start momentum stuff today. If not, we'll end up starting momentum on Friday, which is great because momentum, we're back to vectors again, which means we have to break things into components, yada, yada, yada. But we'll get there when we get there. We have a set amount of stuff we need to cover. The quicker we get through that stuff, it just means we have more review days than if we do. So it lets me move at a kind of nicer pace. So to that end, last class we finished off with, so we were talking about, we had potential energy, was MGH. We connected work and potential energy, so that's somewhere in here. There it is. Work is the negative change of potential. That's just kind of a fun fact kind of thing. Honestly, not a huge deal. I don't think it'll affect too much for you all solving-wise, but it is just kind of a useful thing. So work was the positive change in kinetic energy, and work is the negative change in potential energy. So that's kind of interesting. We then talked about gravitational potential energy. We talked about elastic potential energy. So that's energy stored in a spring. Potential energy, we call it potential because it has the potential to do something. When it comes to gravity, if I lift something up really high, I have the potential that if I let it go, it will start moving. When we talk about a spring, when I squish that spring, it has the potential that when I let it go, it'll start moving. So that's kind of why is it called potential. That's maybe helpful. So elastic potential is 1/2 kx squared. K is a spring constant. That will either be given to you or I will ask you to find it. That is not something you have to have memorized. It's every single spring is different. And X is how far you kind of stretch or squish that spring. Springs, whichever way you do it, doesn't matter. This X can be, and it's whether you squish it or stretch it, just how far away it is from this equilibrium position, it's kind of resting state. That's what X is, and we're going to do some problems with that today. We had gravitational potential energy, that was mgh. M is the mass, G is 9.8, H is how high up you are. I say G is 9.8 for all of your problems, that's true. If you go to a different planet, G changes based on what planet you're on. But all our problems, just to keep it kind of simple, G is going to be that 9.8. Now, I put this, let me actually fix that. Remember when you all do potential energy, positive 9.8. We're going to be using a positive 9.8 here. Do not put a negative in this, otherwise it's going to mess things up. Okay? The only time you all should use negative 9.8 for G is when solving kinematics problems. When solving problems like X, V, T, that kind of thing, that's the only time we put negative 9.8. When we did forces, we don't put negative 9.8 because we had it from the picture. When we do this, it's a scalar, we don't put negative 9.8. Kinematics, because that's always the question. When do I put G as negative 9.8? Only for kinematics. Only for kinematics. X equals VIT plus, yeah.
So if you're using the values of a vector to solve for like a scalar value, you only use the magnitude, and that's true for any scalar?
If you're doing a dot product or a cross product, which is ultimately the way that you convert them, yes. So the question was, when you are converting from vectors to scalars, do you just take the magnitude, i.e. the positive value of it? Yes, with the caveat, when you do that dot product, remember it was cosine of the angle. That angle is what determined whether or not your scalar was positive or negative. Yep. But yeah, we do not put the forces in as positives or negatives. Okay, that's a great question. Okay, so today, and then we talked about kinetic energy a while back. So today, conservation of energy, I introduced the idea of it. Remember, this energy is just a made-up mathematical thing that works. It's very weird. Watch all the videos you want on it. Very weird stuff. But very straightforward. It says that the energy that you start with is the energy you end with. The energy you start with is the energy you end with. It doesn't matter. This is always true. true. This is always true, that the energy you start with is the energy you end with. If we took like the entire universe, the energy that you imagine that the universe started with is the energy that the universe will end with, as far as we understand it, in the entire universe. All that's changing is how the energy is spread out. So like, for example, the sun has a lot of energy stored in it. The sun is emitting light everywhere. It's spreading out its energy all over the place. So the amount of energy that we start with is the amount of energy we end with. That is always going to be true. And then I'm going to kind of build on that just a tiny bit today. So then we did a problem saying if an object is dropped from a height of 10 meters, at what point is the kinetic energy equal to the potential energy? This is a great problem to kind of look through how I did this. But reminder to you all, literally all I did is if I said they're equal, so this is my kinetic energy here on the right. This was my potential energy here on the left. So if I said they're equal to each other, then I just literally replaced the kinetic energy with mgh final, and that let me find the height. You can also straight up just do the math. You could find the potential energy. You can make up a mass. And then at what point are they equal? Well, again, this and this will have to add up to this. If they're equal, it ends up being the same thing. Anyway, great problem to look through, y'all. Great problem to think about. Big fan. Yeah.
Why'd you put them like equal to each other? Like, why'd you put mg10 is equal to mgh?
Oh, because that comes from, so that's a great question. Why did I set the sides equal to each other? It comes from conservation of energy. So the left side of the equation, that mg10, that's my initial energy. And my initial energy, we can see at the top here, is all potential. At the beginning, it wasn't moving. So it was all just mgh. So I put in my h initial, and then at the end, it's mgh final plus 1/2 mv final. Yeah, so conservation of energy, no matter what the problem is for conservation of energy, you'll have to do algebra. Because you basically have two sides of the equation, no variables, isolated. You have to do the algebra to isolate a variable. Yeah. So we'll do some of these examples today. Now, the only thing left that I kind of need to teach you all is if you just have potential and kinetic, it's fairly straightforward. Put all the initials on one side, put all the finals on the other side, kind of solve for what you need to solve for. That's fine. But what happens if friction is present? What happens if air resistance is present? How does that show up in here? It's really simple. And let me make this font a little bit bigger. I actually modified this right before class, so if you did download these, it's going to look a tiny bit different than yours, and I'll tell you what I modified. If we have conservative forces, so conservative forces are ones that you can get back the energy from fairly easily. Conservative forces, kinetic energy, potential energy. No, doesn't matter what kind of potential, as long as it's potential energy, those are conservative. You can go back and forth really easy. A great example of that is a swing. A swing, assuming no friction, would swing forever and ever and ever. And it's constantly going from potential to kinetic, and potential to kinetic, and potential to kinetic. And that thing will swing forever and ever and ever, assuming no friction, assuming no air resistance. Now, what if we have friction? What if we have air resistance? Really simple. Basically, so yes, I wrote something down here, but kind of let me put it a different way. Take the energy that you ended with, take the energy that you started with, subtract those two, and that's going to be the work that friction did. This is kind of the way, and then that leads to this equation over here. So I'll point that out in just a second. Because at the end of the day, so energy is conserved. So again, I'm kind of doing some hand-wavy things here. But what I put over here to the side is basically saying, imagine that I end, let's just make up some numbers. Let's say I end with 5 joules. Let's say I started with 10 joules. The immediate question is, where did the energy go? I had 10, I ended at 5. Where did the energy go? It was lost to friction. That's kind of the mindset here. If you end with less energy, and I'm doing air quotes here because, again, that energy is somewhere. But when it comes to potential kinetic, if you started with 10 and you ended with 5, That energy went somewhere. Where? Friction or air resistance. Could be sound as well, but I'm just basically going to stick with friction or air resistance with you all. And you can see that over on this side, y'all. This is kind of my energy final, and this is my energy initial. Remember that friction, air resistance, always does negative work. We call it negative work because it's kind of like, you can kind of think about it like it's taking energy away. We talked about it mathematically why. Again, it's not, this energy is not getting destroyed. I really, really want to make sure you all know this. When friction steals, in air quotes, steals this energy is not getting destroyed. It's just getting converted to heat, sound, vibrations, stuff like that. You cannot recover that energy easily. You cannot recover that energy lost to friction easily. An easy example, if I slid on the floor, how the heck am I going to get that? That energy is in the ground. How would you even imagine? Try to just think of how you would even begin to get that energy back. It's just not feasible. You kind of lose this energy. Now it's still there. It still exists. I heated up the floor. If you slide on the floor will be a little warmer. So that energy is there, but you can't really recover it. Okay, so that's kind of this whole conservative, non-conservative as well. Another way to kind of think about it and understand it. I'm doing a little bit of hand-wavy kind of explanations here. The wording I'm using isn't probably as precise as it should be, blah, blah, blah. But if that makes sense to you, awesome. That's what I'm going for here. If what I'm saying makes sense to you, that's the end goal. Okay, any questions on this? This is when I told you all last Friday. This is another way to solve those kind of problems where I say, how much work did friction do? You can literally just find the final energy, kinetic and potential, subtract the initial energy, kinetic and potential. Whatever's kind of missing, where to go? Friction. Done. So let's do some problems. We'll start off with ones without friction, and then we'll do ones with friction. Yeah?
Why'd you put it on the left of the...
Yeah, so originally I did have the friction on the right side. I had the work due to friction on the right side. The reason I moved it over to the left is because we need to remember that this work needs to be negative. So by having it on the left side, so if we again imagine numbers, if I imagine that I started, you should always start with more energy than you end with. It is impossible to end with more energy than you started with. Again, you could say something added it, then okay, that should be in our equation somewhere. But in all the cases, yeah, sure, I could technically also put someone pushes something and it adds energy, but that won't be a specific example. So in this case, if I started with 10 joules and I ended with 5, then this work due to friction ends up being a -5. So we get the right sign when we put it on the right side. Yep. And so really, again, it just comes down to, is this work adding energy or losing energy? When it comes to friction, it's always causing it to kind of lose energy, in air quotes. Lose it to the environment, specifically. The system loses energy. The environment, it's always, energy is constant. Okay. All right, so tips. How do you know when it's an energy problem? If there's a beginning and an end. If there's a beginning and an end and things are not colliding. That's kind of the narrative here. When we get to momentum, how do you know it's a momentum problem? There's a beginning and an end and things are colliding. If they're not colliding, it's an energy problem. Make certain you account for all the types of energy. There's literally only 3 types we've talked about. Kinetic, potential due to a spring, potential due to gravity. Those are the only kind of energies. Identify what you start with and end with. Determine if friction is present. If it is present, just figure out how much did I lose. Figure out what I started with. Figure out what I ended with. Whatever I lost went to friction. And that's kind of the narrative for how to go about this. Okay, so let's do a couple clicker questions and then get to some mathy problems. All right, so let's log in, because it always likes to do this to me. So this first question is a spring that's getting compressed. And the question is, what energy do I start with? So when I compress this spring, what energy do I start with? Do I start with elastic potential energy, gravitational potential energy, kinetic energy, or thermal energy? So in the very beginning, at the very, very beginning, what do I start with? So when that spring is compressed, a distance d, what energy do I start with? All right, we'll go to 45 seconds. There's no math here. It's just kind of, do you know what the words mean? Yeah, all right, I'll go a little bit longer because I did hear some people uncertain. So what does it start with? So this is the start. This is my initial. This is my final. So the initial is here on the end, and the beginning on the left side. All right, so I'll go to 1 minute. 5, 4, 3, 2, 1, 0. All right, so this question was actually a little, I'm going to say tricky. It's a little subtle. The first answer is very obvious. Elastic potential energy. It's a spring. If you see a spring, there's elastic potential energy. What's the equation for that? 1/2 kx squared. The next one, gravitational potential energy. Is it above ground? And this is where this one's kind of a little subtle. Fun fact, in every problem you all do with conservation of energy, you get to define where zero is. You get to define where zero is. I highly recommend you all put zero where it's convenient. Now that may sound silly. You may be like, but you told me that the gravitational potential energy at the ground is zero. And in general, when solving problems, that is kind of, if I say find the gravitational potential energy, if I just say find the gravitational potential energy, yeah. And in fact, I will tell you on the test, I will make this promise to you, if I am having you find gravitational potential energy, I will put in there, assume that the ground is zero gravitational, like I'll put that in there. But to this end, what kind of energy does the ball start with? The next answer could be correct depending on if you define this as zero, if you define where it starts as zero, which is my recommendation, we'll see why that's a great recommendation, then no, it has no gravitational potential energy. If you would define the bottom as zero, then it does. So to that end, I will kind of half highlight this answer. I'll give this if you put this one. A couple people did. Technically, you can make the argument that it does start with gravitational potential energy. And we're going to see mathematically why it doesn't matter where you define zero as, but pick it where it's convenient. When we do the problems today, I'll kind of talk through why you want to choose the starting location. It's convenient to often choose that as zero. Or at least you should choose a point that is nice and simple. All right. Now, same question, but I'm asking what does it end with? So this ball, I will tell you that's the highest point it reaches. The highest point. So on that right picture, it's maybe not clear, and that's why I'm telling you all. In the right picture, it has reached the highest point, the apex of its launch. What kind of energy does it have at the apex of its launch? And we'll just go to 50 seconds for this because it's fairly straightforward. Yeah, so this one here, what is the type of energy the ball ends with when it's at its highest point? When it's at its highest point. So when it is at its highest point. That's important to clarify. All right. So we'll close this out in 5, 4, 3, 2, 1. And at its highest point, it is no longer compressing the spring. So nope, none of that. It is, again, if we choose the ground as 0, which is, or if we choose this as 0 or this as 0, either way, it's up in the air. Then it does have that. It is not moving. Velocity is 0 at its highest point, so its kinetic energy is 0. And thermal energy, I guess you could make the argument that it's probably warm and it probably has some energy stored in it. We're going to assume that thing didn't like heat up or cool down on the way up. So yeah.
At its highest point, let's say you removed the spring and it fell to that same 0. Would it all be kinetic energy?
It would all be kinetic energy. Yeah.
If it hit the spring, then you would be building potential.
Yeah, it would. So it would hit the spring, and then it would start to compress the spring all the way back to its original, however much it started compressed. Yep. So it would hit the spring at this point. It would have kinetic energy, and then it would use that energy would get converted into the spring, which is why the spring would get compressed. At the bottom spot, it would come to a stopping point. The spring would be compressed, and then it would launch it back up again, and then it would come back down again, and then launch it back up again, and come back down again, assuming no energy is lost to friction or air resistance. Yeah, assuming no. Technically, whenever a spring gets compressed, you're always going to lose some time.
So when it initially hits the spring again, it's not all the energy.
Yeah, and actually, when it hits the spring again, it actually has potential and kinetic. If we define this as h equals 0, at this point here, when it hits the spring, it has potential and kinetic still because it's above the 0, and then it would compress it. Yeah. So, all right. So to that end, I realized when going through the problem sets that they actually did not clarify some things as much as they should, and I have modified the problems in your favor. You'll see what I mean when I think this is the unmodified version. Yeah, so this is the exact same problem, but we're actually going to do the math of it. So a massless spring of a spring gun has a force constant of K equals 12 newtons per centimeters. When the gun, if you ever see centimeters, we're going to have to convert it. Woo. That's still true. When the gun is aimed vertically, a 15-gram projectile, we're going to have to convert that, is shot vertically to a height of 5 meters above the end of the expanded spring. See below. How much was the spring compressed initially? Okay. So, immediately off, conservation of energy. There's a beginning. There's an end. Things are not colliding with each other. Sure, there's a spring. We're not going to count that as colliding. Colliding will be very obvious. We'll see it when we get to momentum. So it's conservation of energy. Right off the bat, you should just kind of say, yep, I'm going to do that. So we got initial, we have a final. I am going to set up this problem initially in the not as fun way to solve, and the way that actually they did not use, because their wording was not as precise, and I've gone back and changed it. I'll double check that. And then I'll do it the way that actually will have you all solve it. So, okay, what's given? We have K equals 12 newtons per centimeter. I want you all to spend a few seconds thinking about, should this be 1,200 newtons per meter? Or should this be 0.00 or 0.12 newtons per meter? So think about which way should I go? If I need to convert this from newtons per centimeter. I need to convert this to newtons per meter. Will it get bigger by 100? Or will it get smaller? Will I divide by 100 or multiply by 100? Spend a few moments. Think about what you think it'll be. The way to think about this, you could do the math. You can do the math and do the unit conversions and all that kind of jazz. I honestly find doing it the math way harder. Just harder to remember what to do. So how do I think about this? Let's just look at what the units mean. This means for every centimeter I compress this spring, I get 12 newtons of force. For every centimeter I compress this, how many newtons per centimeter? So then all right, let's extend that. If I compress this thing 1 meter, Am I going to get more force or less force? More. I should get more. Because think about it. If I compress this thing a full meter, I'm compressing this thing 100 centimeters. That's a lot. I should have more force if I compress this thing a greater distance. That's kind of the way I logic through it. Which way does it make sense? When I do unit conversions, I honestly just think of which way makes sense. I do not try to do the mathematical kind of thing. Now, if we want to do the mathematical thing, we can do that. If we have newtons per centimeter and we want to convert it to meters, well, I need meters on bottom. I need centimeters on top. And the question is, how many centimeters are there in a meter? 100. The centimeters cancels, and you get the same thing. So you can do it mathematically. You can play with the units and figure that out. Or you can just logic it. Up to you. All right. So great, that's given. We got the mass. That's 15 grams. Remember, grams. It would be great if that's the base unit, but it's not. So we got to suffer through converting it to kilograms. You're going to live in a life, like your whole life, you're going to be converting units, y'all. Because remember, our human brain cannot hold big numbers or small numbers. And so it's not to make you all suffer. It's just because this is useful for you all to actually use different units. Just when it comes to the math, you have to convert them. Okay. Now, here's where we have to make a decision. Where do we want zero height to be? That's the question. Where do we want to define as zero height? Traditionally, we kind of choose the lowest point as zero height. So we can say it starts at an initial height of 0. If we want. That's allowed. We can do that. And that's perfectly fine. Nothing wrong with that. In fact, that's what I encourage you all to do. HI equals 0. I start at a height of 0. Fantastic. What else do we have? We have a final height. Now this is where I kind of point out to you all that the way this problem was originally worded was not actually accurate. My final height is not 5. Yeah, this is why this problem was originally kind of mean, because it was kind of it was subtle. And actually when they solved the answer for it, they didn't take this into account, so I've actually changed the wording to make it nicer for you all. So real quick, I'm going to show you the way this problem is currently worded. The final height is not 5. The final height, if we define this as 0, the final height is 5 plus the distance that the spring is compressed. What does this mean and I'm going to straight up tell you, I'm going to erase this in just a few seconds because we're not actually going to solve it this way. Because this just adds extra algebra with very little benefit. Extra algebra with very little benefit. But I did want to point this out to you all because you do have to be careful about stuff like this. Again, in my class, I'm not going to try to trick you with things like this. But I just wanted to point this out because I think it was an interesting thing that even the person that solved the problem, even the person on OpenStax that solved it, didn't account for. But it does matter. All right, so what does this mean? How do I reword this problem? I'm going to change. Yes, go ahead.
Okay, what did you say? 5 meters above the starting point?
Yes, so I actually changed it, hopefully. I'm going to double check that. Above the starting location. Now, my picture, unfortunately, is no longer accurate because now the 5 meters is actually my final height. So I have changed that for you all because I think there was very little benefit to kind of including that little subtle thing. So anyway, there you go. Final height's 5 meters. This will be much more straightforward, but I did want to pause and recognize that. Fantastic. What else do we know? We know that the final velocity is 0. We know that the initial velocity is 0. Okay. We're going to copy all this stuff over. Kind of work through this. This is actually a fairly simple problem. Even though it seems like I spent a lot of time on it, that's just because I wanted to point it out. I wanted to point out some subtleties here that actually we didn't end up needing. Okay, so we're going to take this, put it over here. It is useful to draw a picture. If a picture is not drawn, a picture can be helpful to help you identify the givens. All right, and boom. Okay. So, what are we solving for? What's the whole point of this problem? This point of this problem is trying to figure out how much the spring is compressed. I know it says D in the picture, but it doesn't say D in the equation. So that's where you kind of have to make that. In fact, D equals X equals question mark. You have to recognize that when we're talking about springs, we're using X for how much it gets compressed, not D. All right, what equation do I use? Conservation of energy. Energy initial equals energy final. At no point in this problem does it say there's friction or air resistance. Therefore, you can assume no friction or air resistance. If there's air resistance or friction, I will tell you. Otherwise, assume there isn't. That's a good rule of thumb for you all to follow in basically most of your engineering classes. All right, so what does that mean? Gravitational potential energy plus spring potential energy plus kinetic energy. Initial equals potential. This is the long way of writing this. So this is the only time I'm going to ever write out every single one. There are literally only 3 types of energy we've talked about, so those are your choices. And we just kind of go through and say which ones exist. In the beginning of the problem, am I above the ground? No. So there's no gravitational potential energy. Don't have to worry about it. In the beginning, am I moving? No. So don't care about that either. So right now I'm just kind of writing it out to show you all that you can just kind of put them all there and think through it. Moving forward, I'm not going to do that. I'm just going to say, hey, here are the ones that exist. The others don't. All right. Do we have gravitational potential energy at the end? Yes. Is the spring compressed at the end? No. Is it moving at the end? No. And this is kind of how you go about solving a conservation of energy problem. Next, we kind of actually write the equations for these. The equation for a spring is 1/2 kx squared. The equation for potential energy is mgh. Super easy, plug and chug. Find x. Yeah. So the energy for, the units for energy would be joules, but in this problem we're not actually solving for energy. We're solving for x. Yeah, how much the spring was compressed. So if we rearrange this, you will find that x equals 2 mgh over k square rooted. You put in the numbers, you hit enter, you get an answer, you say, great. This is one of those that you can think about whether the answer is reasonable or not. If you get an answer that your spring compresses 5 meters, I do not know of any springs that are 5 meters large. That's an unreasonable answer. If you get the spring compresses very little, that could be reasonable if it's a very strong spring. Yeah.
And the original wording of the problem was the height of 5 seconds.
Yeah. Yeah. But I will double check that one. Let me see. Did I already change the wording for you all yet? Okay. I have not. So let's actually fix that. When this gun is aimed vertically, a 15-gram projectile shot at a height of 5 meters above the starting position. And in fact, I actually may have left I may have actually calculated it the other way. So let's just get this number real quick. It doesn't take that long. So x equals square root of 2 times 0.015 times h, which is 5, divided by 1200. Don't forget that square root. I mean, the reality is, I'll tell you all, the spring doesn't actually get compressed that much. Yeah. Is there weird things? Is the answer wrong? Oh, thank you. Yes. I did forget about gravity. Thank you for catching that. That is a very important thing. And if I'd plugged that in my calculator, I'd have a very confused face after doing that. Was that your same? Yeah. Great catch. All right. Fun fact, y'all. It does turn out that the spring. So the answer we get 2 times 0.015 times 9.8 times 5 divided by 1200 comes out to 0.035. Let's see. Is that what the answer says? 0.36. Let me double check that I didn't do something weird at some point. All right. The answer may be off here. All right, someone confirm they also got that answer? All right, great. So I need to go back in here, and through the power of putting a 0, oh, that's why, okay, I did some funky things here. So I'll upload these with the correct stuff. So fun fact, if I'd actually kept the original wording, it actually wouldn't matter much because 0.035 meters compared to 5 meters is so small that the math doesn't actually end up changing much, but whatever. Long story short, here you go. Save. I'll upload that at the end of class, so it's the correct one. Very simple problem. This is like the easiest kind of conservation of energy problem you can get. Okay. A 1 kilogram ball at the end of a 2 meter string swings in a vertical plane. At its lowest point, the ball is moving with a speed of 10 meters per second. What is the speed at the top of its path? What is the tension in the string when the ball is at the bottom and the top of its path? We're just going to focus kind of on part A. Part B is interesting because it involves centripetal force and stuff like that. I'll let you all kind of visit that. But let's draw a picture. We got our ball swinging at the bottom, so it says at its lowest point, it's moving with 10 meters per second. Doesn't matter which direction, left, right, doesn't matter. So it's moving that way, and then, you know, at some later point, it's at some height. And I'm going to check something, because I don't know if this one's even worth doing. Y'all tell me, what's its velocity? I mean, like, there's no math. If you swing this thing at its highest point, 0. So I don't know if this one's actually worth doing. If you swing something left-right, the thing has to come to a stop so it can swing back the other way. So I don't actually know why. Yeah, this one's not worth doing. But what's the answer to A? B equals 0. We did it! Yeah.
What if it's going like all the way around?
Oh, what a good question. All right, I made an assumption here, y'all. I made an assumption that this thing will not reach its highest point. So, what do I have to swing? My backpack. All right. So, that's a great point. If this thing does not reach its highest point, there's no math required and why even do the problem. So like here we go, I swing my backpack left to right, at its highest point it has to stop and swing backwards. But there is nothing in this problem that says it can't be swinging forever and ever and ever and ever and ever. At which point, so there's 2 possible answers here. One requires no math, one requires math. Unfortunately, the only way to figure this out is to do the math. So that's a great point. I made a very bad assumption where you can see in my picture, I assumed it didn't reach the highest point, when the reality is it probably does reach its highest point. So anywho, let's just go ahead and check. We'll find out together. What a fun time. All right, so what's given? We have our mass, which is 1 kilogram. And remember, y'all, this is the cool thing. At no point in this problem does it tell you how high up this ball is. So choose something convenient. What's convenient? Choose the lowest point it reaches as a height of 0. Let's just say it starts at 0. You're allowed. Height is relative. If you all look at the equation, so when we have like potential energy plus kinetic energy, so mgh final, I'm just going to kind of jump to this because I want to show you all what I'm saying. Initial equals mgh final plus 1/2 mv final. Notice, y'all, that you can move kind of the energy to the other side. mgh final minus h initial. Well, if I moved it the other way, let's just move it the other way, whatever. I'm going to erase all this because it's a little messy. When it comes to energy, when it comes to potential energy, specifically gravity, you only care about how high up you went, from the beginning to the end. The difference between 10 and 0 is the same as the difference between 100 and 90. Is the same as the difference between 1,999,990. When it comes to this math, we only care about, it ends up mathematically, we only care about the change in height. So pick numbers that make your life easier. What does that mean? Make the initial height 0. I can make the initial height 1,000,000. My final height would just be 1,000,000 plus however high up it goes. And the math ends up exactly the same. So whatever, pick what's convenient. I am only going to leave this because I don't want to, I'm going to end up writing this again later. So let's just chuck that here for later, for funsies. All right, so we're going to say our initial height is 0. We're going to say down here, and let me draw this, let me move this thing so it's a bit more accurate. We're going to say down here that H initial is 0. I want you all to spend 10, 20 seconds. What's the final height? If I make that initial at the lowest point 0, what's the final height going to be? Spend some time to see if you can figure it out. It is a number that you can find from the problem. And it's not 2. This is a good, I do like this problem because it does make you kind of think a little bit, visualize the problem. That's why pictures are helpful. So picture-wise, I said, what's the final height? So we're trying to find this height. If the string is 2 meters here, and the string is 2 meters here, then my height is 4 meters, okay? If you put the final height as 2 meters, kind of try to figure out why, look back at this, it's a good kind of thing to think through. All right, great. And then we have initial velocity equals 10 meters per second. We are trying to solve for final velocity. We have our equation there at the bottom. At the bottom, I kind of did put all of them. There is no potential energy in the beginning, no potential energy, so I'm just going to straight up erase that. At the end, I have both. It's just a simple math problem. Conservation of energy problems are honestly, mathematically, not bad to solve. There's no vectors involved. It's basically set it up and do some algebra. Conservation of energy problems should be very straightforward. It's a really cool tool. No vectors involved, no angles involved. It's great. So, there's also a really cool thing. This only works if you only have gravitational potential and or kinetic. If you have a spring, you cannot do what I'm about to just do. If you have a spring, you cannot do what I'm about to do. And let me show you what I'm about to do. Every equation here has the same variable in it. Every equation here has an m in it. So the m's cancel out. You could totally plug in the mass and solve this. If I go back to the last problem that involved a spring, the equation for a spring does not have mass in it. So you cannot cancel out mass if there's a spring. You cannot cancel out mass if there's a spring. You cannot cancel out mass if there's friction. You cannot cancel out mass if there's friction. You cannot cancel out mass if there's a spring. Otherwise, yeah, you can. And it makes the life a little bit easier. Okay? I really, it's a nice shortcut, but I don't want you all to use this, and you may actually need to cancel out the mass. I may not give you the mass in a problem. But, there you go. All right, 9.8 times h final, that's 4, plus 1/2 VF squared. So VF is going to equal, subtract the 9 point, I'm just going to do it all in one go on my calculator, which is a little bit dangerous, but it's fine. Times 2, square root it. And lo and behold, your fellow student was correct. This thing does make it around the circle. We would find out that if this... So how would you know whether or not this thing made it around the circle? You would try to be taking the square root of a negative number, and it wouldn't work. You would get a calculator error when trying to solve this if it didn't make it all the way up. Part B is kind of a good review. I'm not going to spend the time on it, but it's centripetal force. The forces, free body diagram, normal force, gravitational force equals mv squared. It's a good one to do, just to make sure you all don't forget. Remember, the final is cumulative. So it is good to do these ones, even if they're not going to show up the next test, to make sure you remember it. Yeah.
So the final velocity, that's going to be the velocity at its highest point.
Yeah, at its highest point, it is moving. It is going to keep swinging around. Yep. Yeah, that's a great question. And an interesting one with, like, an interesting question for this problem would be like, how fast do I need to spin this thing so it just barely makes it to the top? Would be kind of interesting as well. But not going to ask that here. All right, I think I have one more. Let's see, does this last one work? This last one I'll kind of set up, and then next Friday we'll get started on momentum. It'll be fun. And there's ghosts. All right, so I'll save this. I'll go to the next slide, read through it, give you all a chance to kind of think of the givens, and then I'll make the ghosts go away. A boy throws a ball of mass 0.25 kilograms straight upwards with an initial speed of 20 meters per second. When the ball returns to the boy, its speed is 17 meters per second. How much work did air resistance do to the ball during its flight? I like this problem because it also, it kind of utilizes an idea that we talked about before. So week 7. And this one's actually very easy to do. Super easy problem. Okay. So he throws it straight up with initial velocity of 20 meters per second when it returns. So immediately, hopefully you all look at this and say, hopefully you recognize that there is air resistance, because if you all remember from us tossing something upwards, if I toss something upwards, if it comes back to my hand, it should have the exact same velocity. If I toss it upwards with 20 meters per second, it should return with 20 meters per second, assuming no air resistance. Assuming no air resistance, something returns to your hand at the same speed it leaves with. Well, clearly it didn't return to the same speed. Where'd the energy go? To the air. And you don't get back that energy. It's now in the environment. All right, so let's just do this real quick, set it up, and then we'll call it good. So our mass is 0.25 kilograms. You need the mass to solve this. This problem is impossible without me giving you the mass. The initial velocity is 20 meters per second. The final velocity is 17 meters per second. We are solving for the work that air resistance does. Work air. How do we do this? I know I'm kind of lightning McQueen because I got 1 minute. Kinetic energy initial plus the work due to air equals kinetic energy final. 1/2 mv initial squared plus the work due to air equals 1/2 mv final squared. You plug in the numbers. 1/2 times 0.25 times 20 squared plus the work due to air equals 1/2 0.25 times 17 squared. Notice this number is bigger than this number. The work due to air will be a negative answer. Why? Because it's in the friction. Air resistance always makes a force opposite the direction of motion. Air resistance and friction are always doing negative work because they're always opposite the direction of motion. Do the rest of this, prove that to yourself, have a great time. See you on Friday for Momentum. Yeah, and if you have any questions, feel free to come on down. But I won't hold you all any longer.